and this is going to be the first part of 2 on the immune system. And our first part is going to talk about the innate immune system. We decided we'll talk about the innate immune system first, just as response for those people juniors who won't be in class here on Tuesday, because the adaptive immune system is a little bit more complex, and so I thought this would be a good starting point. So this goes primarily with section 35.1 in your textbook. So first of all, overview of the immune system in general. The immune system is responsible, or is a collective host of defenses that the body has to protect itself from foreign invaders or foreign matter from entering the body. It doesn't just exclusively act on pathogenic invaders, but anything that's foreign or your body recognizes foreign and not belonging to itself, it defends against. So it could be a harmless piece of foreign material, like in the case of allergies, where it's not necessarily pathogenic. Your immune system will still try to fight it off. When invaders first breach the outside of an organism, get into your body, the defenses ramp up and become much more drastic. In general, your immune system uses molecular recognition to differentiate self, so part of its own body, from that foreign material. There are 2 types of immune responses that we're going to talk about. Today, first we're going to talk about the innate immunity, or the innate immune system. And this innate immunity relies on a small number of receptors that generally target molecules that are not found in animals. So not very specific. And it's basically saying this is us, this is self, versus this is not self. And that's in kind of contrast to what we'll talk about next time, the adaptive or acquired immunity, which relies on thousands and thousands of specific receptors for different pathogens. So we're going to look at this top part here today. Look at this top part here today, the innate immunity. So things we'll be talking about are barrier defenses and internal defenses. And some characteristics of this innate immunity is recognition of traits shared by broad ranges of pathogens, and it's a rapid response. Alright, so this top part of this infographic is what we're going to focus on today. Next time, the bottom part. So the first part of our innate immunity that kind of goes with this box right here is called barrier defenses. All animals have an innate immune system, and barrier defenses are that first line of defense against foreign invaders. So barrier defenses pretty much prevent pathogenic or foreign material from infiltrating your body to begin with. One of the biggest for humans is the skin. It is a physical barrier that prevents organisms from getting into your internal environment. Couple that with the fact that your skin has a pH of anywhere between 3 and 5, that acidity inhibits most fungal and bacterial growth. So the pH of your skin on top of it just being a physical barrier helps with that barrier defense. Mucous membranes in your mouth, in your intestines, things like that, line internal cavities and trap pathogens as well before they can infect really your internal environment. Lysozyme, so digestive enzymes found in things like tears and other secretions like sweat and sebaceous glands, kill off bacteria by breaking their cell walls. So they contain antibacterial enzymes. The low pH of your skin and your stomach also denatures enzymes and prevents them from proliferating. And then your natural gut flora, so good bacteria in your gut, outcompete a lot of bad bacteria that might inhabit there for food. So all of these are examples of the barrier defenses, the first kind of physical defenses your body has from pathogenic invasion. Next, your body has what's called cellular innate defenses. So once a pathogen enters your body, so is able to get to the inside, several innate defenses are there to combat them. One of the biggest innate defenses are phagocytic cells, so things like neutrophils and macrophages engulf and destroy invaders, and this is an example of a macrophage. And what these macrophages have on them are little receptors. They're called toll-like receptors. And what toll-like receptors do is they recognize non-native proteins on viruses and bacteria. And when a pathogen, for example, binds with that toll-like receptor, it causes this pathogen this phagocytic cell to engulf this pathogen by endocytosis, like we talked about in our cell unit. So through endocytosis, it brings this in the vacuole. And then a lysosome, so phagocytic cells have tons of lysosomes with digestive enzymes. That vacuole containing the pathogenic material fuses with this lysosome. The lysosomal enzymes destroy the pathogen. And once it's destroyed, via exocytosis, it releases the debris. So this is general how phagocytic cells digest pathogens. Toll-like receptors bind to non-native proteins, becomes via endocytosis, fuses with a lysosome, pathogen is destroyed, debris is released. Eosinophils are also another type of defense cell that helps to defend against multicellular invaders. An example is eosinophils. Will become very active. Your eosinophil count, like a CBC, will show increased eosinophil fraction if you have like parasites or parasitic worms. And last, natural killer cells that circulate in your blood release destructive chemicals to destroy a wide range of viruses and bacteria. So when they are activated, or their receptors sense or bind to viruses or foreign bacteria, they release a host of chemicals that circulate in your blood that then destroy those foreign pathogens. Here is a picture of a toll-like receptor. Here's like toll-like receptor 5 that binds to flagellin in bacterial flagella, or toll-like receptor 4 that binds to a lipopolysaccharide that's found in bacteria. And these toll-like receptors stimulate vesicular formation or endocytosis of that pathogen to destroy it. Antimicrobial peptides and proteins are also things that your body secretes for the innate immunity. So interferons are substances secreted by cells that are infected by viruses. So if a cell, like this one, is infected by a virus, that causes the production of alpha and beta interferons. And what interferons do is they signal near other cells nearby that haven't been affected, and they tell those cells to do specific things or make specific substances that will then destroy or inhibit bacterial propagation and replication. So for example, when a virus infects this cell and starts to use the cellular machinery to replicate, it also triggers the interferon mRNA to be translated into alpha and beta interferons. These then travel outside the cell to stimulate a neighboring cell to begin transcribing and translating antiviral proteins that degrade the viral DNA and prevent them from replicating. So interferons are one antimicrobial peptide or protein, and the complement system is another. And the complement system is just a wide number of circulating proteins, all are inactivated, just circulating in the blood. And when a pathogen contacts them, certain proteins are, activate, and the activated form leads to the destruction, the bursting of those pathogens. Well, interferons and the complement system are two types of antimicrobial peptides and proteins. Lastly, there is the inflammatory response, and we're all very familiar with the inflammatory response because this is when things swell. Like if you hit your thumb with a hammer, or you get an injury and it starts to swell up, bee sting, things like that. It's a set of events triggered by trauma or infection that causes swelling, redness, and tenderness, and it's part of your innate immunity. So, for example, let's give the scenario like in your book that a splinter gets stuck in your skin, and on the splinter there's a host of pathogens or non-native microbes. And your inflammatory response is going to respond to those foreign invaders. So what's going to happen first is, in this area, macrophages are going to come or aggregate in this area to try to engulf and destroy a lot of that foreign material. And when they encounter those foreign materials, their toll-like receptors bind to pathogens. They're going to release chemicals called cytokines. These are signaling molecules that then recruit other cells to that damaged area. Those cytokines stimulate increased blood flow to the area, for the walls of the capillaries to become leaky, and this is what's responsible for triggering a lot of those symptoms of inflammation. The hotness and redness comes from increased blood flow, and it starts to swell up as fluid and other white blood cells move from the capillary into the surrounding tissue. So a lot of anti-inflammatory medications block cytokine signaling. Other things that end up being recruited are mast cells. Mast cells increase histamines, and these cause your capillaries to become leaky. So they become like spaces in between the capillary walls. And this allows other macrophages and phagocytic cells, neutrophils, things like that, to be able to go from the blood into the surrounding tissue to start chewing up those foreign particles. So it's good that your capillaries become leaky so that those cells can go to the site of infection and digest the pathogens. However, that's responsible for the swelling as well. We could get into talking more about, how a plaque is formed and kind of walls off this area, and a scab is formed via fibrin, but not as important for what the AP test wants you to know. One thing that's good to point out is you can have localized inflammation of something like the splinter, or maybe due to a bacterial infection, you can have systemic inflammation, where large parts of your body systems are becoming inflamed. And systemic inflammation can often lead to what's called septic shock. And what happens in septic shock is profuse secretion of histamines causes a major blood vessels to become leaky like this. and fluid to travel into the surrounding spaces. So we've got some edema, peripheral edema happening, and that because we're losing fluid from our blood vessels, our BP goes way down, and that's what ends up being really dangerous. Septic shock happens when we lose a bunch of that blood volume. Might result in heart failure, and really dangerous. I mean, especially really old and really young. Systemic infection can very easily cause septic shock, which would easily cause death. But this is kind of the end of what we're talking about, the innate immunity. So after we talked about the inflammatory response here, those are the sections for innate immunity, and the next section we'll talk about for next time will be part 2 for our coverage of the immune system in chapter 35, the adaptive or acquired immunity.